This video is to talk about some of the different statistics that we've been calculating and their distributions. We're going to use this to go through a problem and see some of the differences between z and t. Alright, so let's start where we normally have started, looking at the sample mean. Right, the expected value of our sample mean is mu. And now if we have a variance given to us, if we know the population variance, sigma squared x, then we can use it. We're going to use it in the standard normal distribution, and you've been calculating z-scores much like this. Now this equation might look a little bit different than what we've seen before, but if we just take the square root of sigma squared x over n and simplify it, it results in this equation. And the way that we do our confidence interval is we have to know what our alpha level is, and then we have to look up the z-score that corresponds to that alpha level, where half of that alpha is left over in each of the tails. Then we just take our sample mean plus or minus that z times our standard deviation divided by root n. Now, if we don't know the population variance, that doesn't change the expected value of our sample mean. But we are going to calculate this sample variance s squared, and it'll look like this. The way we normally calculate variance is take each x, subtract the mean, square it, add it up, and then we previously divided by n, but for the sample here, we're going to divide by n minus 1. We're also going to use the t-distribution, and remember that the t-distribution changes depending on the number of degrees of freedom. So our number of degrees of freedom will equal our sample size minus 1. So just like we calculated a z-score up here, let's calculate a t-score, and we do it in basically the same way. Alright, we take root n times x bar minus mu over n here. This is just the standard deviation that we're using when we don't know the population variance. Alright, so it corresponds with this. And this is basically if we took the square root of s squared x over n, we could simplify and get this. Now if we do a confidence interval, here it changes just a little bit. We have our mu is going to fall between x bar plus or minus, and here instead of a z-score, we're going to have a t-score. And instead of our population standard deviation, we're going to have this sample standard deviation, and we divide by root n. But you can see that the process is very similar. So now, let's look at the population proportion if we have a large sample, right? This p hat is roughly the equivalent of our x bar. Remember that what we need is some sort of binomial trial where we have success or failure, right? And we take our number of successes divided by n equals p hat. Now the variance is going to equal p hat times 1 minus p hat over n. We've done that before. We can use the standard normal, and we can calculate our z-score like this. We've done that plenty of times before, and if you would prefer it in a different form, it can look like this. And now the confidence interval, p is going to lie in between p hat plus or minus. We're going to use z because this is the standard normal distribution. You've got to look up the 1 minus alpha value for that, and we're going to multiply by sigma p hat. So you can see that this is very much the same thing as we've done for the others, where we start with basically our sample estimate, and then we have this margin of error over here that we have to add and subtract. So let's go through a sample problem over here. All right, let's look at how z is different than t. So we're going to have a sample mean of 1100, a sample size of 10, and let's get a 95% confidence level. Okay, so the first case is we know the population standard deviation is 100. The second case is we don't know the population standard deviation, but we find our sample standard deviation is 100. So we want to compare these two confidence intervals. So let's write down the information that we know. All right, so we saw that x bar equals 1100. And we have a sample size n equals 10, and we want the 95% confidence interval. Okay, well, for part A of this question, we know that the standard deviation, sigma x, is equal to 100. In part B, we don't know sigma x, but we know that our sample has a standard deviation of 100. All right, so we don't know anything about the population. So what that means is that for part A, we are going to have to use the standard normal, and for part B, we'll have to use the t-distribution. So let's go through this. On A, we want to find a confidence interval for our mean. It'll be centered around x bar. We're going to add and subtract. Now we're going to take z of 1 minus 0.025, right? That's alpha halves. Here we have alpha equal 0.05 for the 95% confidence interval. And we're going to multiply this by sigma x, and we're going to divide by the square root of n. Now for part B, our confidence interval will also be centered around x bar, but what we add and subtract is different. This time we're going to take the t of 1 minus 0.025, and also note that here we have 9 degrees of freedom. Okay, so our sample size is 10. Okay, so n minus 1 equals our degrees of freedom here. Next, instead of multiplying by sigma x, we only know sx. So that's what we multiply by, and again, we divide by the square root of n. So let's just go ahead and plug in numbers for all of this. Okay, so this is going to be x bar is 1100 plus or minus z of 1 minus 0.025. When I look that up, z 0.975, I end up with a z-score of 1.96. All right, and I'm going to multiply that by 100. And then I'm going to divide by the square root of 10. Now down here for part B, start at 1100. And then the part that we're going to add and subtract, this margin of error, is going to be the t value. So I have to look at the t table at 9 degrees of freedom. And then I look up at the top of the table and I see the 0.975. And I find that value equals 2.262. All right, and then I'm going to multiply that by sx, right here is 100, and once again divide by root n. Okay, so now this part up here, the top, our confidence interval is going to be 1,100 plus or minus, and then this fraction right here, if we work that out, is 61.98. And down here we have 1,100 for part B plus or minus 82.91. Now, let's take a look. What do we notice about these numbers, right? So what we're comparing in part A, here is our margin of error, and in part B, here is the margin of error. So what's going on is we can see that in part B, we have more wiggle room in this confidence interval than we do up in part A. And that should sort of make sense. If we don't know the population variance, then down here we have to estimate it using the sample variance, and we're just not so sure as we are up here, and that's going to lead to our confidence interval being larger.